Greetings, everyone, and welcome to chemistry. Today, we're going to be learning how to solve for the heat of reaction using the table above for these independent heats of formation. Keep in mind that heat and enthalpy are going to be used interchangeably, and all of the heats are presented in kilojoules per mole. So in order to solve for the heat of reaction, essentially what we have here is delta H of reaction equals the total heat of the products minus that of the reactants. So the first one's pretty easy because they all have ones as coefficients. So the hard part is just looking at the chart and trying to find each one. So let's look for sodium hydroxide. So sodium hydroxide in the solid phase is negative 426.7. Then we're going to add hydrochloric acid. So it's HCl. And let's see if we can look for that one as well. Where is HCl? Oh, there it is at the very top. Minus 92.3. That's a point. All right, so then let's go to the product side. Sodium chloride in the solid phase is negative 411. And then water in the gas, don't get messed up. It's not going to be the liquid water. It's going to be the solid. So let's do minus 241.8. Now they're all in kilojoules, so I'm going to keep, there's no need to have to write all the units for every single one of these. So let's do delta H of reaction. The delta H is going to be the product. So let's group all of the products together. If we were to add 411 plus negative 241, that would get essentially subtracting a negative. So you're going to have a negative 652.8. And then let's subtract we have the total products, and then we have to subtract the reactants. So what is the reactants? The reactants, if you were to subtract those, you would get 519, negative 519. So it's important to note that the negative symbol represents an exothermic reaction. Heat is being released. All right, so if we have a negative, negative, ching, ching, we have positive, positive. So what is the total going to be? We're going to have negative, and then we have a positive. So the delta H is going to be negative 133.8 kilojoules. And remember that this is going to be an exothermic reaction at the end of the day. Perfect. So easy peasy lemon squeezy. Let's start, and let's actually do the next one. So I'm going to clear, so you may have to pause, but I'm going to clear everything. And let's go to the next one. Perfect. Let me zoom in here. All right, so the next problem is a little bit trickier. Number one, they left off one of the amounts in the table. Number two, there is going to be twice the amount of heat. So please keep in mind that we have twice the heat here, twice the heat there, because we have twice the molecule. We have twice the matter, twice the heat. All right. So now this is not on the table. It was an oopsie. So if you are not watching the video, you can be very confused. We have negative 1110. Now oxygen, since it's not present, is going to be a 0. And then please keep in mind, since there's twice the matter, we have twice the heat. So we're going to have to multiply by twice the heat there. And then we're also going to have to multiply by twice the heat for carbon dioxide in the gas phase. So we have twice that of negative 390 3.5. All right, so let's get our formula. So we have the products. Let's multiply 2 times negative 393, negative 393.5 times 2. So we are going to have a negative 787. Subtract that of the product. So you should have, it should be 210, but let's just double check. I'm sorry, 220, good thing I double checked. 220, and remember that's gonna be negative. So then those are going to be negative, negative. Those are gonna turn to positive. And then let's find products minus reactants. So negative 787 plus 220 equals negative 567 kilojoules. 567 kJ. And remember that's going to be exothermic. Exothermic. And that's it.